Hi all, I am Anil Anadi. Here I am going to talk about quantized conductance that we have seen in quantum point contact devices that are embedded in LAVSTO nanowires. And this work is done at University of Pittsburgh in Professor Jeremy Levy's lab. Yeah, we are working with LAVSTO interface, which has been known for novel phenomena at the interface, where the high mobility electron gas at the interface along with the superconductivity at millikelvin temperatures and magnetism in various phases at the interface. Yeah, the interface also has a sharp insulated to metal transition at about 3 layers of LAO on top of STO, and this insulating phase can be made into conducting by applying a positive gate voltage through strontium titanate on the 3-unit cell LAVSTO interface. Further, the interface conductivity can also be controlled by a conducting AFM technique that we have used for writing these quantum point contact devices also. So here the insulating 3-unit cell sample can be made into conducting by applying a positive gate voltage. So I'm gonna show in the coming slides the writing process here. Yeah, so nanowires were made with this conducting AFM technique, and these devices have shown enhanced mobility at room temperature compared to the normal LAVSTO 2D samples. Further, recently we have also made quantum cavity quantum dot devices using this technique, which has shown a signature Coulomb blockade structure, which is a characteristic of quantum dot devices. So we further interested in understanding the ballistic nature in these quasi one-dimensional structures. So we believe this is very important to understand or realize some of the topological phases such as quantum Hall effect and edge states in these LAVSTO nanowire devices. So to realize this ballistic transport, all we need to have a nano construction in the form of nanowires or quantum point contacts, where the density of states are tunable and possesses one-dimensional subbands. So the signature to realize the ballistic transport is to observe the conductance quantization, where the conductance appears in a integer numbers of a quantum number. So we aim to make these nano constructions at the LAVSTO nanowires. So we use this conducting AFM technique to write these nano construction point contact devices. So I'm gonna play a video here how we made our device. Basically, we write the nanostructures along the interface connected electrode in a specific geometry, as is shown here, and the positive voltage to the tip basically creates a conducting paths, and negative voltages creates basically locally erases the conducting lines or creates insulating regimes. Yeah, so our device geometry for this quantum point contact devices is shown here. Basically, we write first the connecting electrodes by applying a positive voltage to the tip, and this is actually our active device, where it consists of conducting nanowire written first. On top of it, we have two weakly insulating barriers which are created by negative voltage to the tip, and somehow this constriction, as shown in the picture, works well as a quantum point contact in this study. So this is our measurement geometry. We use the four-probe method to measure the conductance in the active device. So the figure shows our device tunability with the side gate, which we use one of the written electrode as a side gate, where for the positive values the conductance of the device increased by increasing current in the device. We analyze gate bias spectroscopy on the device. Basically, uh, we measure the conductance by sweeping the source drain bias at various side gate values ranging from 0 to positive values. So in the main graph, so what we see here is that near the zero bias, the conductance curves converges to a value which is roughly coinciding with integer values of the conductance. So the bottom curve shows the zero bias conductance obtained for various side gate voltages, where again we see a sort of plateau like behaviors in these devices, whereas when we applied a magnetic field to the device of 9 Tesla, this quantization gets clearer, and which is also evident from here that, and the values are exactly corresponds to the integer values of quantum number. So this data shows that our device is having a ballistic transport behavior. Further, we measured magnetic field dependence of these zero bias conductance curves in the magnetic field range of 0 to 9 Tesla here, and we see two specific behaviors where the low fields, the plateaus appears to be near 2e square over h, whereas at the higher magnetic fields of 9 Tesla, they are perfectly matching to the 1, 2, 3, 4 e square over h values. We further analyze the transconductance data, which is obtained by doing a derivative of the conductance. The data is shown here. So it is clear from this data that actually the first e square over h plateau is splitting from 2 e square over h, and the 3 e square over h plateau is splitting from 4 e square over h values. So we attribute this further plateau splitting is appearing from Zeeman splitting of these subbands. For example, in the absence of magnetic field, so in the first subband, the spin up and spin levels are degenerate, so one would expect 2e square over h value when near the zero bias. Whereas when we turn on the magnetic field, actually the spin up spin down band splits depending on the strength of the magnetic field and Z factor of the device. So that's why we see a integer e square or h plateaus in the presence of magnetic field. To extract the G factor, further we analyze the transconducting data at various magnetic fields. So basically the energy separation that we need to extract the G factor can be obtained by analyzing or estimating the delta E value by doing a finite bias analysis, where basically delta E corresponds to the 4-terminal source drain bias, which is equals to the spacing between two spin bands. So we extracted a G factor using a relation by fitting the delta E versus B linear fit, and we found that G factor is about 0.5 for these devices, and also we estimated that the spin plating energy is about 30 microelectron volts per Tesla for these devices. We further measured the temperature dependence of this quantized behavior, and we see that this quantization persists up to 700 millikelvin, and above that we saw a disappearance of this behavior. The thermal activation energy for the particular temperature is about 60 microelectron volts, and which is in the order of the spin splitting that we have seen. Yeah, we further made longer devices just to see how far this conductance quantization persists and electrons scatter without any scattering. And we see uh, this quantization in the devices as long as 600 nanometers, where for these devices at higher magnetic fields we still see a quantization of the conductance. So this we believe very interesting for investigating some of the exotic phenomena such as topological phases in these LEO-STO interfaces. To summarize my talks, we say that we successfully made quantum point contact devices that are embedded in these LEO-STO nanostructures, and we demonstrated the conductance quantization in nanoscale devices of length even up to 600 nanometers, and we also see an integer conductance quantization at higher magnetic fields which imply a spin resolved transport, and we believe this will be crucial for investigation of topological and edge state modes in these LEO-STO nanowire devices. Thank you very much.